It's all very nice to talk about specific heat and how to measure it and to demonstrate the transient state using ping pong balls and that sort of thing. But this doesn't really tell us anything about how to apply this concept to animals and plants living in the real and quite variable world. What we're going to do now is to introduce a quantitative measure of the transient state, which we can then use as the basis for exploring larger issues of inhabiting an unsteady world, where the transient state is the norm. That measure is known as the time constant. We're going to learn what it is and how to quantify it from transient state data like we obtained for our ping pong balls. We're going to have to get a little bit mathematical. Sorry, but there's just no way around it. But I'll show you some tools later to make all of this easier and more relevant. The basis of analyzing the transient state is the exponential decay curve. This describes how something comes to equilibrium over time. Let's put it in terms of coming to temperature equilibrium. We plot a temperature of something, say a body, symbolized with the uppercase T, and time symbolized with a lowercase t. Starting from an initial temperature, T sub 0, the temperature will decline following this curve as it asymptotically approaches the equilibrium temperature, T sub infinity. A well-established equation describes this curve. The temperature at any time t, or T sub t, will equal the difference between initial and equilibrium temperatures multiplied by the base of the natural logarithm, e, raised to the power of minus time over this quantity, symbolized with the Greek lowercase ta. Phew, that's quite a mouthful, but it's worth it because it gives us what we need, the time constant. The time constant is the time it takes for the temperature to decline to equilibrium divided by E. Let's make this a little easier, and I'll soon be making it easier still. In the example I just showed you, we chose arbitrary initial and equilibrium temperatures. But what happens if we choose different temperatures, or if the body was heating up instead of cooling? No problem. We can make this more general by replacing the temperature scale with what we might call a dimensionless temperature. This is the ratio between the difference of temperature at any time t and the equilibrium temperature divided by the difference between initial temperature and equilibrium temperature. By expressing all transient temperatures as dimensionless temperatures, all transients will now vary between an initial value of 1 and an equilibrium value of 0. And this will be true no matter what the initial and equilibrium temperatures are, or whether the temperatures are rising or falling. Here's the exponential decay curve equation rewritten in this way. The time constant is now the time it takes for this ratio to approach 1 over E. We're not quite over the mathematical hump yet, but things are going to start getting easier, I promise. Let's first rewrite the exponential decay curve by taking its natural logarithm. Here's what the equation looks like now. It actually is simpler. What was a complicated exponential equation is now a linear equation of the natural log of dimensionless temperature versus time, with a slope of minus 1 over tau. Work out the equation for yourself. It's quite easy. Let's plot the dimensionless temperature on a semi-logarithmic plot. The curve starts at 0 and has a slope of minus 1 over tau. The time constant is minus 1 over the slope. We can also estimate tau graphically. The time constant is the time at which the natural log of the dimensionless temperature is minus 1. Okay, that's pretty easy, but what about the time constant? The time constant indicates a rate of approach to equilibrium. How rapidly something approaches equilibrium is expressed by the slope, which is proportional to the time constant. If the line has a steeper negative slope, this indicates a shorter time constant and a faster equilibration rate. If the slope is shallow, this indicates a slower equilibration rate and a longer time constant. Turning back to the original exponential decay curves, faster time constants correspond to faster approaches to equilibrium, faster equilibration, that is. How fast the equilibration rate is has some significant ecological implications. Okay, let's get back to some data. Just to refresh our memories, here are the data for warming and cooling of the black ping pong balls making the transition to full sun, followed by the transition to full shade. As previously, the white triangles refer to temperatures of the hollow ping pong ball, that is, the one with low thermal capacity, and the green diamonds refer to the high thermal capacity ping pong ball filled with water. Let's now estimate the time constants for these two transitions. We'll do separate graphs for the transition to full sun and another for the transition to shade. The y-axis is the natural logarithm of the dimensionless temperature of the ping pong balls, and the x-axis is the elapsed time in seconds. In the transition to full sun, the high-capacity sphere follows this course. You can see clearly that the data have been linearized. The best fit straight line for these data shows the time constant to be about 13.3 seconds. The low-capacity ping pong ball heats much more quickly. The best fit straight line for these data gives a time constant of about 1.1 seconds. In the transition to shade, the time constants are much different. The high-capacity ping pong ball follows this linear course, and the best fit straight line gives a time constant of about 21.9 seconds. As before, the low-capacity ping pong ball has a time constant on the order of 1.01 seconds. So that's an example of the transient state and how to calculate the time constant from temperature data when there's a transition from one condition to another. It's important to emphasize that this applies to a transition from one environment to another. It's the transition that gives you the transient state. There's no such thing as a transient state in constant conditions. When conditions are constant, everything comes to equilibrium, and that's the steady state. Okay, we've been through a lot of math and data manipulation. The time constant in and of itself is an interesting number to have, but I've put you through all the math and analysis because the time constant is so much more than the number itself. In fact, the time constant is the starting point for a number of very powerful tools we can use for analyzing the transient state.